Lift a stray snowflake to lamplight and watch a miracle of arithmetic unfold. 6 arms grow in lockstep, each branching at the same 60-degree cadence, each cradling sub-branches that echo the parent form. The secret is water's hydrogen bond. 2 slight positive charges cling to 1 negative oxygen like outstretched hands. Fixing the angle between neighbors at 120 degrees, stack those molecules into solid lattice, and a hexagon appears by geometric inevitability. Yet symmetry alone doesn't birth individuality. As the crystal drifts through turbulent pockets of humidity and temperature, growth speeds vary along its arms. Diffusion-limited deposition accentuates edges, slows recesses, carving fernleaf tracery unique to a single moment in the cloud. A snowflake, then, is a diary of atmospheric whims written on a template of molecular symmetry. 6-fold order supplies the grammar. Micro-instability writes the poetry. Once the flake touches your sleeve, its delicate hierarchy sublimates. But for a heartbeat, you hold evidence that cosmic laws guide even the lightest whisper of winter. Shift your gaze to a grain of table salt under a microscope. You'll find an endless city of cubes. Chloride anions and sodium cations alternating like tiled streets. Slide that lattice 1-unit cell to the right, or upward or into the page, and the scenery repeats without change. This invariance under translation forms the heartbeat of crystallography. In 1912, Max von Loewe pierced zinc blende with X-rays. The scattered beams converged into a speckled constellation on photographic film. The lattice imprint in reciprocal space, von Loewe's pattern, decoded atomic positioning more precisely than any ruler could measure. Today, synchrotron rings achieve the same feat in microseconds, revealing new polymorphs for catalysts and battery electrodes. All rely on symmetry's clarity. When the arrangement repeats perfectly, waves interfere constructively along specific angles, broadcasting the crystal's internal poem to the outside world. But perfect periodicity does not forbid creativity. Quartz twists its helices, calcite splits light in perovskites fold octahedra. Each variation, a different verse within translational meter. Like music constrained by time signature yet free in melody, crystalline matter translates symmetry into endless functional motifs. From strengthened diamond to piezoelectric song and sonar ceramics, slide deeper, and electrons themselves become poets in a periodic landscape. In free space, an electron may adopt any wavelength. Inside a crystal, its wave function must harmonize with lattice spacing. According to Bloch's theorem, allowed energies cluster into bands separated by forbidden valleys, band gaps. These gaps are not arbitrary. They arise because electron waves reflecting off repeating ions can interfere destructively, much as noise-canceling headphones. Quiet a steady hum. Silicon, arranged in diamond cubic symmetry, hosts a gap of 1.1 electron volts, wide enough that at room temperature electrons sit quietly in the valence band, yet small enough that a trace of phosphorus can tip them into conduction with modest voltage. Pion junctions, solar cells. And every logic transistor on Earth function because this gap is neither too wide nor too narrow, but exquisitely just so. Alter the symmetry, compress silicon, alloy it with germanium, twist it into 2D sheets, and the gap shifts, tailoring infrared detectors or high-speed lasers. Thus, the smartphone in your pocket is a triumph of symmetry engineering. It converts bits to music, maps, and memory by choreographing electrons across structural repeats measured in angstroms. The next time you tap a glass screen, remember, the click of information begins in the silent rhyme scheme of silicon's crystal lattice, patterns solid yet invisible. Born from the same geometric insistence that sculpts every snowflake drifting beyond your window. Peel a single layer from pencil graphite, and you reveal graphene, a sheet 1 atom thick, stitched into a honeycomb so faultless that engineers call it two-dimensional, which carbon bonds to 3 neighbors at 120 degrees, repeating a hexagon across kilometers of potential film. In that symmetry, electrons forget they have mass. Their energy-momentum curve sharpens to Dirac cones. Twin funnels that meet at a point where charge carriers sprint at 1/300th the speed of light. Twist one graphene sheet atop another by a magic 1.1 degrees and more patterns emerge, enlarging the unit cell 1,000-fold. The symmetry softens, the Dirac cones flatten, electrons slow to a crawl and, almost lazily, pair into superconducting states at temperatures once thought impossible for carbon. Valley symmetry, once trivial, becomes a quantum label engineers can tweak with gentle strain. Birthing valletronics where information might flow, not by charge but by which side of a Dirac cone an electron occupies. Thus graphene is a paradoxical gift. Symmetry so perfect, it grants particles near relativistic freedom, yet flexible enough that a mere twist spawns new phases of matter. A mundane pencil stroke hides a playground where geometry dictates not only form, but future technologies. Transparent circuits, quantum sensors, perhaps even room temperature, superconductors waiting in the angles between hexagons. Hold your palms together, identical outlines, yet mirror images that refuse to overlap. Molecules share this handedness in life for reasons still debated. Chose sides. Every amino acid in your muscles and neurons twists to the left, every sugar in your DNA spirals right. Flip the orientation, and enzymes stall. Receptors misfire, metabolism grinds to a halt. How did biology pick its favorite glove? One clue lies in meteorites such as the Murchison Fall, where the amino acid serine appears in a left-handed excess. Perhaps circularly polarized ultraviolet light, filtered through star-forming clouds, destroyed right-hand molecules more readily, seeding Earth with a modest bias. Autocatalytic chemistry could then amplify that 1% lead into total dominance, like a single snowball, triggering an avalanche. Physics whispers an even subtler hint. The weak force violates mirror symmetry. In beta decay, electrons emerge preferentially left-handed, imbuing space with a minuscule chirality. Calculations show the resulting energy difference between left and right-hand amino acids is far too small to drive selection directly, but enough, perhaps, to tip a cosmic coin when chemistry teetered on the edge. Whatever the origin, homochirality makes biology possible. Proteins fold because identical hands clasp in predictable ways. DNA zips because sugars twist uniformly. The next time a heartbeat echoes in your chest, remember it is orchestrated by a left-handed. Bias written not only in cells but in the breaking of a universal mirror eons before the first spark of life. Symmetry can also break in real time, weaving living tapestries from simple rules. In 1952, Alan Turing, better known for code breaking, proposed that two reacting chemicals diffusing at different speeds could paint stripes, spots or spirals, on an otherwise featureless sheet. Today we watch reaction diffusion waves roll across Petri dishes, cobalt blues blooming into rings of yellow, and splitting into leopard-like rosettes, mathematics written in pigment. Look skyward at cumulus clouds boiling above a hot plain. The hexagonal cells of rising air are a Rayleigh-Benard convection pattern. Asymmetry under vertical translation shatters when temperature gradient exceeds a critical value, forcing orderly rolls to channel the heat. On a grander canvas, Jupiter's Great Red Spot and the spiral arms of galaxies follow similar hydrodynamic equations. Proof that instability can sculpt structures across 80 orders of magnitude. Even your own skin bears Turing's signature. Zebra bands, leopard rosettes, the whirl of a fingertip. All trace back to molecular gradients that broke uniformity in the embryo. Tiny asymmetries at a cellular scale balloon into macroscopic identity. The difference between a tabby stripes and a cheetah spots is the ratio of diffusion constants for two proteins. Thus, from laboratory beakers to planetary storms, patterns emerge not by blueprint, but by symmetry that can no longer hold. Blossoming into order as beautiful as it is inevitable, echoing the cosmic fractures that once seeded galaxies, now replayed in every raindrop swirl and seashell spiral. In 1982, Don Sheckman cooled an aluminium-manganese alloy and aimed an electron beam through the newly formed grains. The diffraction pattern that bloomed on his screen carried tenfold symmetry-sharp spots, arranged in rings like a celestial mandala. Classical crystallography declared the image impossible. True crystals repeat at regular intervals. Such repetition forbids 5, 8, or 10-fold rotational orders. Yet the pattern was unmistakable. The alloy was a quasicrystal ordered, but not periodic. Its atoms occupy a mathematical tiling, akin to Penrose patterns. Two rhombuses, and ratios of the golden mean, filling space without ever repeating. Walk the atomic arrangement, and you never meet the same environment twice. Yet long-range order persists, reflected in those sharp diffraction peaks. Quasicrystals blur lines between solid and art. Their periodic order yields low thermal conductivity and unusual surface friction. Today, they harden non-stick cookware, reinforce steel gears, and inspire architects who weave Penrose tilings into glass facades. Forbidden symmetry, once dismissed as error, now stands as proof that nature's vocabulary extends beyond perfect repetition, speaking fluently in patterns that are ordered but forever new. Hold a sprig of Romanesco broccoli. Each turret mimics the whole vegetable, spiraling in golden ratio whirls that repeat across scales. Such fractals arise when symmetry is broken, not in space but in size. Zoom into a river delta, a lightning strike, or the alveoli of a lung, and the branching geometry echoes itself. An iterative mantra marching toward invisibly fine detail. Benoit Mandelbrot gave these shapes their name and the mathematics to describe them. Feed a simple complex number equation through endless feedback and the now iconic Mandelbrot set appears: coastlines, spirals, dendrites, nested within one black heart. The fractal dimension, a non-integer measure between line and plane, quantifies how rugged a form remains as you zoom. Coastlines lengthen, clouds gain area. Networks of neurons pack immense surface into small volumes, optimizing diffusion of nutrients or thoughts. Fractals teach engineers, antennas patterned on the Sierpinski gasket resonate on many frequencies. Fracture analysis of metals uses self-similar crack fronts. Computer graphics compress mountains and coastlines with recursive algorithms. Symmetry in scale does not show as harmony, but as boundless complexity and ode to imperfection repeated again and again. Why do humans find symmetry soothing? Neuroscience suggests our visual cortex fires more efficiently. When patterns mirror or repeat, less metabolic fuel is spent predicting the next curve. Yet perfect regularity becomes boring. Music stuck on a single chord. Architecture locked in sterile grid. Artists and architects instinctively insert broken symmetry. A jazz syncopation. The staggered facati of Gaudi's Casa Batlló. The off-center pupil in a Renaissance portrait that breathes life into marble calm. Evolution exploits the same sweet spot. A peacock's tail is broadly symmetric, signaling genetic health. But each feather's micropattern deviates just enough to prove it is real, not parasite, distorted mimicry. Flowers advertise nectar with radial balance that guides bees, yet slight petal irregularities distinguish one species from another, steering pollination fidelity. Thus our sense of beauty is a dialogue with symmetry, not a worship. We crave the familiar rhythm so our brains may rest, then the unexpected twist so curiosity wakes. In snowflakes, crystals, even Lombardi spiraled galaxies, nature composes that aesthetic innately, inviting us to resonate with patterns that whisper both order and organic surprise.